The statement that adding a ground fault circuit interrupter, or GFCI, to an ungrounded service provides sufficient grounding protection downstream is incorrect. Grounding protects against electrical shock by providing a low resistance path for fault current to flow to the ground. GFCIs, on the other hand, detect small imbalances between the hot and neutral wires and trip the circuit if a fault current is detected. In ungrounded systems, there is no grounding path for fault current. When a GFCI is installed in an ungrounded system, it can only detect fault currents that flow through the GFCI itself. Fault currents that flow through other paths, such as appliances or damaged wires, will not be detected by the GFCI and will not trip the circuit. Using GFCIs as a substitute for proper grounding in ungrounded systems can create a safety hazard. In the event of a ground fault, high voltage can flow through the GFCI and into downstream receptacles. This can result in electrical shock or fire. The National Electrical Code, or NEC, requires that electrical systems be properly grounded for safety. For ungrounded systems, the NEC allows the use of GFCIs as a temporary measure, but it requires the installation of a grounding system as soon as practical. Adding a GFCI to an ungrounded service does not provide sufficient grounding protection and is not in accordance with electrical code requirements. Proper grounding must be installed to ensure the safety of electrical circuits and occupants. It is important to understand the difference between grounding and GFCIs. Grounding provides a path for fault current to flow back to the source, tripping a circuit breaker or fuse and energizing the circuit. A GFCI, however, detects small imbalances in current and trips the circuit to prevent electrical shock. In an ungrounded system, a GFCI can only protect against shock if the fault current flows through the GFCI itself. It cannot protect against shock if the fault current flows through another path, such as a person touching a faulty appliance. Therefore, it is crucial to have a proper grounding system in place to provide comprehensive protection against electrical shock and fire hazards. The NEC provides specific guidelines for grounding electrical systems, including the size and type of grounding conductors, the methods for connecting grounding electrodes, and the requirements for bonding metal parts of the electrical system. These requirements are designed to ensure that the grounding system is effective in providing a low impedance path for fault current. When working with electrical systems, it is essential to consult the NEC and follow all applicable safety regulations. This will help to ensure that the electrical system is installed and maintained in a safe and reliable manner. Ignoring grounding requirements can lead to dangerous situations, including electrical shock, fire, and equipment damage. Always prioritize safety and consult with a qualified electrician if you have any questions or concerns about grounding or other electrical issues. In summary, GFCIs are a valuable safety device, but they are not the substitute for proper grounding. In ungrounded systems, GFCIs can only provide limited protection against electrical shock. To ensure the safety of electrical circuits and occupants, it is essential to install a proper grounding system that meets the requirements of the NEC. Grounding ensures a low resistance path back to the source for electrical shock. If there is a fault, current will want to go back to the source of the energy. The grounding wire ensures that there is a dedicated path back. GFCIs detect imbalances, meaning that current is going somewhere else other than back. If that happens, it trips. But in ungrounded systems, there is no grounding path for fault current. So when a GFCI is installed, it can only detect faults that flow through the GFCI, but not others. It is a safety hazard if you use GFCIs in ungrounded systems because high voltage can flow into downstream receptacles, resulting in electrical shock or fire. The National Electrical Code requires that electrical systems be properly grounded for safety. If it is an ungrounded system, the NEC allows the use of GFCIs as a temporary measure, but it needs a grounding system as soon as possible. As such, adding a GFCI to an ungrounded service does not provide sufficient grounding protection and is not in accordance with electrical code requirements. Proper grounding must be installed to ensure the safety of electrical circuits and occupants. Think of grounding as a highway for electricity to return safely in case of a fault, and a GFCI is a sensitive monitor that detects any abnormal detour of electricity, but only within its immediate vicinity. The absence of the highway, the grounding system, makes the GFCI's ability to protect significantly limited. Let's delve into some additional details to paint a clearer picture. Firstly, the purpose of grounding is to provide a safe, low-impedance path for fault current to return to the source, typically the transformer. This low-impedance path ensures that a large fault current flows, which in turn causes the overcurrent protective device, like a circuit breaker or fuse, to trip quickly, disconnecting the circuit and preventing dangerous voltages from persisting on metal parts that could be touched. Secondly, GFCIs operate on a different principle. They constantly monitor the current balance between the hot and neutral conductors. If there is a difference of 5 milliamps or more, indicating the current is leaking somewhere, potentially through a person, the GFCI trips very quickly, typically within a fraction of a second. This rapid tripping action minimizes the duration of the shock, reducing the risk of serious injury or death. The limitation of a GFCI in an ungrounded system is that it relies on current flowing through it to detect a fault. If the fault current takes a different path, bypassing the GFCI, it won't detect the imbalance and won't trip. Consider a scenario where an appliance with a faulty internal wire touches its metal casing. If the appliance is plugged into an ungrounded receptacle protected by a GFCI and a person touches the metal casing, the fault current might flow through the person to ground, bypassing the GFCI entirely. In this case, the GFCI wouldn't trip and the person would receive an electrical shock. The NEC recognizes the importance of grounding and provides detailed requirements for establishing a grounding system. This includes the use of grounding electrodes, such as ground rods or metal water pipes, connected to the grounding conductor system. The grounding conductor system then connects to the metal enclosures of electrical equipment and appliances, providing a path for fault current to flow back to the source. While the NEC allows the use of GFCIs in certain situations where grounding is not feasible, such as in older homes with ungrounded wiring, it is always recommended to install a proper grounding system whenever possible. GFCI should be considered a supplementary safety measure, not a replacement for grounding. In conclusion, the claim that adding a GFCI to an ungrounded service provides sufficient grounding protection is a misconception. GFCIs and grounding serve different purposes, and GFCIs cannot compensate for the lack of a proper grounding system. Always prioritize safety and ensure that electrical systems are properly grounded in accordance with the NEC and other applicable regulations. Remember, electricity is a powerful force that can be dangerous if not handled properly. It is always best to consult with a qualified electrician if you have any questions or concerns about electrical safety. Furthermore, let's consider the implications of using a 3-prong tester on a 2-prong receptacle protected by a GFCI. These testers typically work by creating a small current flow to ground. In a properly grounded system, this current flow would be detected by the grounding system and would not cause the GFCI to trip. However, in an ungrounded system, the tester might create a path for current to flow through the GFCI, causing it to trip. This does not necessarily mean that the GFCI is providing adequate protection. It simply means that the tester is able to detect the presence of a GFCI. The fact that the GFCI trips when tested does not guarantee that it will protect against all types of ground faults. As mentioned earlier, the GFCI can only protect against faults where the current flows through the GFCI itself. If the fault current takes a different path, the GFCI will not trip, and the person could still receive an electrical shock. To reiterate the NEC stance on ungrounded systems, it's crucial to understand that while GFCIs can be used as a temporary safety measure, they do not fulfill the requirement for a complete grounding system. The NEC prioritizes the installation of a grounding system to ensure a safe and reliable electrical environment. GFCIs are seen as a supplementary protection method, offering an additional layer of safety, but not replacing the fundamental need for grounding. It's also important to remember that electrical codes are not static. They evolve to reflect new knowledge, technologies, and safety concerns. Therefore, it's essential for anyone working with electrical systems to stay updated on the latest NEC requirements and best practices. Consulting with a licensed electrician or electrical inspector can provide valuable guidance and ensure that electrical work is performed safely and in compliance with applicable codes. Ignoring code requirements or attempting to circumvent safety measures can have serious consequences, potentially leading to electrical shock, fire, property damage, and even loss of life. Safety should always be the top priority when working with electricity. In addition to the points discussed, it's important to emphasize the importance of regular GFCI testing. GFCIs are mechanical devices that can fail over time. The NEC recommends that GFCIs be tested monthly to ensure that they are functioning properly. Testing a GFCI is a simple process that involves pressing the test button on the GFCI and verifying that it trips. If the GFCI does not trip when the test button is pressed, it should be replaced immediately. Another important aspect to consider is the proper installation of GFCIs. GFCIs should be installed by a qualified electrician who is familiar with the NEC requirements for GFCI installation. Improperly installed GFCIs may not provide adequate protection and could even create a safety hazard. For example, if a GFCI is installed in a location where it is exposed to moisture, it could malfunction and fail to trip when a ground fault occurs. Similarly, if a GFCI is installed in a circuit that is overloaded, it could trip frequently, causing nuisance tripping. Nuisance tripping can be annoying and inconvenient, but it can also be a sign that there is a problem with the electrical system. If a GFCI trips frequently, it is important to investigate the cause of the tripping and correct the problem. In some cases, nuisance tripping can be caused by a faulty appliance or a wiring problem. In other cases, it can be caused by electromagnetic interference, or EMI, from other electrical devices. EMI can interfere with the operation of the GFCI and cause it to trip. If EMI is suspected, it may be necessary to install a line filter to reduce the EMI and prevent nuisance tripping. In addition to GFCIs, there are other types of ground fault protection devices that can be used to protect against electrical shock and fire hazards. One such device is the arc fault circuit interrupter, or FSI. FSIs are designed to detect arc faults, which are a common cause of electrical fires. Arc faults occur when there is an unintentional electrical discharge between two or more conductors. These discharges can generate high temperatures that can ignite nearby combustible materials. FSIs work by monitoring the current waveform in the circuit and detecting patterns that are characteristic of arc faults. When an arc fault is detected, the FSI trips the circuit, interrupting the flow of current and preventing a fire. FSIs are typically installed in bedroom circuits and other areas where there is a high risk of fire. In conclusion, the use of GFCIs in ungrounded systems is a complex issue that requires careful consideration of the NEC requirements, the limitations of GFCIs, and the potential safety hazards. While GFCIs can provide some degree of protection against electrical shock, they are not a substitute for proper grounding. To ensure the safety of electrical circuits and occupants, it is essential to install a proper grounding system that meets the requirements of the NEC.